Hello, physics, and actually probably hello, drama people that aren't here to see this. We're going to continue on our adventure in sound. We got a lot to cover today, and hopefully we can get a number of things done and kind of do this. So the last stuff we talked about was the speed of sound is dependent upon the medium that it's in, because all waves, the speed depends upon the medium. Sound is no different. And so sound actually travels pretty darn fast in solids, and not too bad, 340 meter per second in air. That's not too bad. If you ever seen a plane fly overhead, you'll see the plane say here, but then you hear it well behind it, because sound takes time to get to you. It's pretty awesome when you think about it. But and in the book on page 405, we're going to use that today. It's a table of data that your homework will just reference or will say, how do you do this problem? And you're like, I don't have enough information. Didn't you know you're supposed to look at page 405? No, you didn't tell me. And it just doesn't care. Anyway, so 405 has a table of data, speeds of sound, different things. So you notice they've got speed of sound in air at 0 degrees, at 20 degrees, at 331, then 343. So it does increase with temperature, 0.6 meter per second for every 1 degree Celsius. So now let's use our knowledge of mechanical waves and discuss these next questions. What is an echo? Like in sound. What is it in comparison to the other stuff we talked about? All right, so when a wave reaches a boundary, what does the wave do? One of three things. Either reflects back, goes forward through, or splits and does both, right? An echo is a reflected wave. That's all that it is. It's a reflected wave. We have incident waves and reflected waves. It's a reflected wave that's actually a sound wave. That's all an echo is. That's why in the Sprinky lab I probably referred to him as an echo when I was down there with him. Like, oh, look at that echo. Echo is because this is just it's a reflected wave. Now, have you ever, for instance, right now, I'm on a recording, you ever heard yourself speak and gone, that's not me, who is that person using my words? You do sound different on recordings, that's not an illusion. Anybody know maybe why that is? For the way the voice gets to you, the medium that it travels through. When I'm speaking, my vocal cords are down here in my chest area, and so those things go and they send the pulses out. Well, that pulses travel through me to get to my eardrum where I'm going to be hearing it. Well, how do they get there? They get there by traveling through this 10-pound meat sack right here known as my head. And anytime that sound is traveling through a different medium, it's going to sound different. You ever tried to talk underwater? Doesn't work so well, does it? It's like what is that? I don't know. But you hear yourself through your meat, but not entirely through your meat. Because if you put your hands over your ears and talk, you sound different, don't you? No, you sound a little different. So what you're doing is most of the sound you hear of your own voice comes through your flesh, but some of it actually does come on the outside and comes into your ears. That's what you can block out when you cover it with your hands. So whenever you hear yourself speak, you are the only person who hears it the way that you do. Everyone else hears the part that's coming in your ears, the part that's on recordings, the stuff that goes through the air, but you hear the stuff that vibrates through your meat. The only way someone else is going to hear you exactly is if they stuck their ear inside your flesh somewhere and listened. Then it would sound just like you. Yeah, the question I was asked, because you probably didn't hear it, is everyone agrees that I sound the way I do except me. I'm the only... Yes, that's true. Everybody hears the exact same person but you. You hear someone else. You hear it differently. You can hear what they hear by recording yourself and then listening to it. That's the only way to know how you sound like. You hate... Right, most people don't like recorded them just because it's not someone they've ever talked to or heard before in their life. They've never heard that voice before. It's because everybody's voice is unique to them. There's way too much in the construction of the human body to make duplicate voices. So you just hear, like, who's that stranger? I've never even met that person before. So you just have this natural, I don't like this voice. It sounds awful. Everyone else is like, you sound fine. You sound like everyone else. So I'm just going to put on here 10-pound meat sack. And I think that will explain that. Okay, sonar. You guys know what sonar is? They send sound out and they figure out how far away things are. Okay? We're going to pull up just a real quick clip of the Hunt for Red October. There's a submarine out, Russian submarine over here. We're an American submarine here looking through periscopes. and the American submarine is sending Morse code to the captain of the Soviet submarine, and the Soviet commander responds with a sonar ping, and you get to hear it in this. So those of you who are watching the recording will probably hear nothing. So just use your imagination, or type this into, you can watch it yourself.
Will he be the only one looking for the periscope? Probably. U.S. told you intend a missile launch. Break. Do not approach U.S. coast or you will be attacked. Break. If intention is other, will you discuss option? Break. Can he acknowledge with a single ping?
Yeah, he can. Question is, really?
And here's Sean Connery, the Russian sub-commander. You know, will he... It's like, verify our range. And they hear it in the ship over here. So, we'll stop it right there. Anyway, so sonar, you're gonna be homework problems and stuff with sonar in it. But for instance, if you have a boat which will look like this, because most boats that have sonar look like that. No, and you have a floor or something like that down here, an ocean floor. Well, when that sound wave goes out, it's going to strike objects and then echo back. Since I can know the speed of sound in water and seawater, well, we got that chart there, it's 1533 meters per second. So I know the speed. Oh, that's not a 3, that's an M. 1533 meters per second. If I know the speed of sound, and then I know how much time it takes from a pulse to when I hear the echo, I know rate and I know time. So guess what I can find? Distance. And I can know how far away that thing is. Now, in actual sonar, you don't have people sitting with calculators constantly spam calculating this thing, okay? You have a computer so the thing is sending out multiple pulses and getting all these echoes back, and that computer is doing the division, getting the numbers, and then generating a graph of the image. And so when they're out searching for like a search of a wreck or something like that, they can just look at a screen and get an image of what the bottom looks like, computer generated. And you can find all kinds of stuff. You can also find submarines. You can find underwater sea mines. You can find whales, like, because they're big enough you can get that echo back. Yeah. I think back in the day it was so the question was, is it audible sound? Today I don't think so. I think most sonar's done. You can't hear it. In that film, the old Soviet submarine in the 70s or whatever, big pulse like that, and you could hear it. I don't know if that's a dramatization or not. I don't know. But it's cool because, like, pew, pew, yeah. Yeah, quiz will be on Chapter 15 next week. Yeah, I will not. You do not have to memorize any of these numbers. Thank you. The 343 you're going to use all the time, just like 9.8. You're just going to end up memorizing it because you can't help it. Sorry. It's going to get in there. But the rest of them, no. Don't worry about memorizing any of those. Now... loud spots. So how sonar works, it's an echo and D equals RT. Okay. Be careful in the homework problems. If they give you the total amount of time from pulse to return, you got to divide by 2 if you're looking for the distance, because the time traveled is doubled. Okay, so you've been at a Life Change Week, or if you've been at a concert or whatever, and sometimes you might feel like, man, this music is super loud. Why is it so loud? And someone else is like, I didn't think it was that bad. Now it's only like 2 rows behind you. Like, what was wrong with you? There are patches, and so they try to design places like this to avoid things like that. But if you have 2 speakers, and they're sending out sound waves, wow, 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 wow. Somebody over here could hear it, and someone over here can hear it, and someone over here. But someone all of a sudden is like, why is it super loud here? There can be a spot here and a spot over there and a spot over there where the sound is incredibly loud. Any idea why that happens? You have 2 waves coming together at the same spot. What can happen when waves occupy the same spot? Constructive interference. And destructive interference can happen too. There are quieter spots in the stands. And I forgot to get this video ready, but I can show you later. you can actually rig these guys up in such a way that you can have them completely cancel at a certain spot. And so standing over here on the left side, you hear music. Standing over here, you hear music. Standing right here, you hear nothing. It is cool. It's cool. We did it at Purdue, and it was pretty awesome. But you have to link the things together and make sure they're broadcasting at the same time. And then you can set distances and find a nodal line where the standing waves are completely canceling. Anyway, so sound can do wave interference. Okay, constructive and destructive. And sound can do standing waves. That's what all of Section 15.2 is about. Music. And it's awesome. How does music happen with wind instruments, the string instruments, and things like that? We're going to get into some things in the next section where some of you will know a little more than me, I got a feeling. But you're just going to nod and tell me yes or no to certain things. Okay. So that's a bunch of that. Ready to do a couple problems real quick? Just like, what are the homework problems looking like? All right, here we go. Boom. I said boom. There we go. Question 1. What is the wavelength of an 18 hertz sound if it's in seawater at 25 degrees Celsius? What is its wavelength? Well, what do I know? I know the frequency. Yeah, I know F. 18 hertz. That is a sound lower than the human ear can hear. It's actually so deep that you can't even hear that low. It's awesome. We'll play with that later today too, what the ear can hear. But how do I find wavelength? What's the relationship between F and lambda? Flamda. Not flemda, that's gross. Flamda. So if I know the speed of the sound, which, hey, guess what? They said seawater, 25 degrees Celsius. That's a very specific medium. That's in our chart, 1533. So 1533 meter per second. We've got a frequency of 18 hertz. I want my lambda. Oh, my lambda. That's for you, Bailey. And you're not even watching this because you're not in drama. I'll have to remember to do that joke tomorrow. Okay. 5.2 meters. Okay. So sound, which is pressure and then anti-pressure and then pressure. Between the first piece of pressure and the next spot of pressure is 85 meters. Even though things are going woo, 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 it's just the sound is traveling so fast. It's 85 meters between pulses. It's pretty sweet. Okay? Next question involves an adventure into my childhood. That is not what I need. Google Maps. I need a mouse. I'm going to have to do all of this, and you guys are going to hear nothing. So I'm going to pause the recording, and we'll... Alright, so yeah, if you shout at a barn on a normal spring afternoon, and you hear the echo, 0.8 seconds later, how far away is the barn? So what do we know here? We're going to need to know the speed of sound off the table. Yeah, 343 meter per second is how fast sound travels at room temperature, which is a normal spring afternoon. We know that the total time it takes to go down and back is 0.8 seconds. It's an echo. I produce the sound, meh, makes it to the barn, comes back, meh, and I hear it come back to me. So we're gonna have to divide by 2 at some point. I can either divide the total time by 2 because it means it takes 0.4 seconds to travel down, or I could do the total seconds of total speed and I would get the total distance down and back, then divide by 2. Either way, I'll get the same answer. So I like to just divide the time by 2. It makes more sense in my head. So then we'll use dirt, and we do 343 meter per second times 0.4 seconds. And survey says... yeah, 137 meters from the road to the chicken house where I was making my sounds as a child. All right. You gotta grow up in the country sometimes. Good times. Okay, let us continue on our adventures. Next question I'm going to have for you is, actually, did I put it right here? I did. Whoopsies! You hide that. You didn't see nothing. Okay? That's how much blood I've given. Leave that alone, too. Let's advance. I need new slides. There we go. Okay. how do we build things to detect sound? Okay? How do we actually detect sound? Now, you've got two organs attached to the sides of your head that detect sound, but if you wanted to build a machine to detect it, now sound goes in and out. I'm going to grab something here. I'm sorry, 1 second. So I have air going back and forth. How am I going to build something to detect it? Okay, air is not a lot of particles, so what are we going to do? I need to have something that moves with it. I need to have something that would move with that air. So what I could do is have some kind of sail, maybe, some kind of flap. I don't know, something that would then, when the air moves through it, the flap would move back and forth. And then maybe with that flap, I need to have that attached to something that it could pull on, maybe, send an electrical signal, or something like that. I don't know, but that way I could at least pick up whether or not, so maybe this is a wire, and this goes to some computer, I don't know. And I could then at least detect when the thing wiggles. Now, there's a couple things that I need to take care of. The first of all is it's going to take quite a bit of air maybe to make that flap move. I got to make it super, super sensitive, right? Super thin so that it actually will move. But the problem is if I make it really, really thin, then a slight breeze could tear the thing in half. That wouldn't be good. So it needs to be pretty strong material, but pretty light material. And that's going to be kind of tough because even some sound waves is such a light little movement, just out and in, out and in. I may not be able to pick it up if that thing doesn't move. But maybe if I stick it in a column, and so that all of the air going in would then take that flat, all the air going in would focus to one spot, and then that thing would move with that all that air focusing in, I could get I could hear it better. I could get a better detection. And so if we use a long tube like this, or in the case of a microphone, which we use to detect sound, you have a bunch of these little in the head. Google that stuff. I'm not talking how to build mics. But anyway, we got the air itself funneling into this thing, the pressure wave, out and in, out and in, out and in, out and in. It gets to this guy, which we got a nice seal here. So this thing's going to go out and in, out and in, out and in. It's still going to be maybe a little weak. And then how do I wire it? If that wire's clipped on there, then that's going to tear that right away. So, but if we attach to it maybe something solid, something like, some kind of metal or something solid, maybe wood, and I actually go ahead and attach it to it or make it part of that. That way when the whole thing moves, you've got this flap that's sensitive enough to move, but you've got something solid attached to it that can move and then do something. And then maybe this thing I could have doing something with it. I could, to make it a little louder, I could use lever and I could use torque. And whenever I push this thing forward, this thing here is going to come backward. And if I put the fulcrum, say, right here, then a small torque here is going to make this a long arm here and a short arm here. So that way, if I put my fulcrum here, I get a lot of torque here. A little motion here is going to get the same amount of torque over here. And I could have that thing striking something else. So I could have a multiplier in there. It may seem like crazy, but this is what's inside your head. And it's happening in real time right now. The human ear has, we're going to watch a little video of this. You've got the big pinna, which is this flabby part that is actually has the right curves in it to help focus the sound to come straight into that hole in your head. And yes, it actually is a hole right into your head. And so in this hole, it goes back, we've got the tympanic membrane, aka your eardrum, back in there. And then attached to that eardrum are these three little bones, Shadrach, Meshach, and Abednego. They're the three smallest bones in your body. And whenever you have the malleus, the hammer, moves, the incus is now providing leverage. The stapes is a small circle with two little bones attached on it like this. And that whole thing, it looks like a hamburger masher, if you've seen one of those. Like two metal parts, but it's a circle on the bottom. And that piece here starts banging against the wall. And so the waves are coming in, and that thing starts pounding against the wall. Well, what good is that? This is all one way to pick up the sound and then amplify that sound using leverage. This guy is where the magic happens, the cochlea. And so to understand the cochlea, well, I'm going to show you the video. How's that sound? Because that'll make more sense. So I'm going to have this video playing. For those of you watching online, you're just not going to hear much. I'll try to, I don't know. There's nothing I can do. Sorry. Just enjoy. Or Google this.
To understand the ear,
we need to understand what sound is. The speakers you are listening to right now are vibrating, flexing in and out, causing a wave of pressure through the air. The frequency of these waves, or the speed at which the sound creating surface moves back and forth, affects the pitch of the sound. The level of air pressure in each wave is directly related to how loud the sound is. The outer part of our ear catches these waves. It faces forward and has a specially designed structure of curves helping us to determine the direction of the sound and also emphasize the frequencies used in human speech. Now that the sound waves are caught, they travel through the ear canal and strike against our eardrum, a thin membrane about 10 millimeters wide. Now that we receive the sound, the middle ear transfers this energy. The smallest bones in your body, the malleus, incus, and stapes, start in motion. The malleus is attached to the eardrum, and as the sound travels along, the force is amplified by leverage until it arrives at the stapes, which acts like a reverse piston, creating waves in the fluid of the inner ear. The most significant increase in pressure is caused by pneumatic amplification. The face of the stapes has a surface area of about 3.2 square millimeters, while the eardrum has a surface area of 55 square millimeters. Using this, along with leverage through the malleus and incus, the final pressure is 22 times greater than when the sound first arrived. Now we come to the most complicated part of the hearing, the cochlea. In reality, it is coiled up, but it is easier to understand straightened out. There are actually 3 chambers inside, but let's take a look at the central part. The stapes is causing pressure waves to travel through the structure.
I should interrupt you right here, just as one part is full of all the electrical parts that run your ears. One part's full of fluid that actually gives you balance. Why that's in the ear, it's a good question. And the last part is due to the sound, hearing part. So, sorry, it's just like fluid, electrical.
The stapes is causing pressure waves to travel through the structure. Along the inside wall is about 20 to 30,000 reed-like fibers. As the waves move along, they encounter fibers with the correct resonant frequency and energy is released. These fibers aren't actually what give us the signal that we heard something. There is a special structure next to these fibers containing hair cells. When the fibers resonate, they cause the hair cells to move, which then sends an electrical impulse to the cochlear nerve and onto the brain. Certain pitches of sound will resonate in specific locations, and louder sounds will cause more hair cells to move. Our brain interprets all this raw data, making it possible to enjoy things like music or an engaging conversation. Just to think that all of this is happening in your head right now at full speed. This is just one of the amazing systems found in the human body that go far beyond our humble human understanding.
All right, we're going on an adventure. So, the way that sound is perceived, the frequency of the wave is what we call pitch. So the higher the frequency, the higher the pitch is. If a 50 hertz sound is incredibly low, you can't even produce it as a human. That's like 100 hertz or something like that, the lowest, whatever. But we can hear almost about a 16,000 hertz. That's just going to depend on the quality of your ears. But as you get older, that 16,000 cap eventually makes its way down to about 8,000, and you lose about half of your upper range. But if you listen, we just listened to a sound test, that upper range I'm fine missing out on. It's a horribly high-pitched sound that I don't ever care about. But you may have seen those old fogey detectors, which is just something you could play with your phone, and it makes incredibly high-pitched sound, and all the young people go, what is going on? And the old people don't even hear it at all. Yeah, that's because it's beyond the 8,000 mark. Once you reach about 40 or 50, you just start losing that. So anyway, but pitch is depend on frequency. So when I go meh versus mrr, it's how many waves per second are coming out. Okay, good. So that's one thing that sound is perceived based on its frequency. It's also perceived on its amplitude and some other fun things. So for amplitude, amplitude of the wave is how we perceive as loudness. Okay, so if we think about, so back in the old, and when you had waves, I'm just going to draw it like this, even though sound is a longitudinal wave, transverse is usually a little easier. But the amount of waves per second, the frequency of the wave, that's how high pitched it is. But how far away you go from the nodal line, that's how loud it is. So why really loud sounds can hurt your ears is because you have an extreme amount of pressure coming into this little tube here. And at that pressure, that crazy amount of pressure gets here to that eardrum is going to be moving farther and farther with that pressure as the pressure gets increasing, and you could eventually blow your eardrum, or you can actually tear that piece, and you can go deaf eventually. So why are some people deaf? It could be a problem with this, it could be a problem with the bones, it could be a problem with the cochlea, it could be a problem with the nerve heading to the brain. If it's a problem with the nerve heading to the brain, we don't have anything to fix that. But if it's a problem in here where it's just they're starting to get like, oh, I can't hear as well as I used to, what we can do is we can put a hearing aid in here that simply takes the sound that comes in and amplifies it and just plays it louder. And then they can hear it because we're just sending sound in there louder. But if something in the mechanics in here goes wrong, depending on what it is, there are cochlear implants. They actually have things they can replace these guys with to make it pick up. It's crazy. Wow, hearing technology has gone on. But it can hurt the ears. The amplitude hurts the ears, but there are also certain frequencies, you don't have to write that down, that will actually take you into the threshold of pain. So just certain frequencies like cat nails on chalkboard. Like, ah! Doesn't have to be that loud for it to hurt. It's just like, ah! Yeah, question. So, okay, so the question was, how does a hearing aid do any better if it's louder? So if you have, for instance, something here where this is just weaker, or inside here the fluid is more thick, and so that way when there's supposed to be vibration of the molecules just aren't moving very much. They're just like barely going. But if you make the sound louder, then they're going to be going enough that it detects it. So yeah, if the eardrum blows, you'll have to have some kind of surgery to fix that. And they've got stuff for it. It's amazing. Do you guys know where this tube goes? It goes in your mouth. Isn't it awesome and disgusting? It goes right into your jaw. That's where your body drains stuff. Yeah. So you have, like, see, you have earwax and stuff, and you have all this gunk and everything. They're like, we need to flush that somewhere. Let's just sit it right in your mouth. It's nothing. It's just, what, did you, okay, so I gotta pause the video. Now when it comes to measuring that loudness, you may have heard of decibels before. So because we can hear a really, really wide spread of sounds, a really, really low amplitude to incredibly high amplitude, we use a logarithmic scale. In chemistry, we took the logarithm of hydrogen ion concentration to get the pH scale, running from 0 to 14-ish. We have a logarithmic scale for sound as well, for the Bell system. And so the loudest audible sound, you're going to want to write that guy down, is 0 decibels. Decibel is named after the inventor of the telephone. Who is that? Alexander Graham Bell. Decibel, you've heard of decibels? Decibels? They're named after Alexander Graham Bell. They're actually decibels, but no one says decibels in the Midwest. Decibels. No one says decibels probably anywhere. But they're decibels. Say decibels. I won't be offended. Anyway, 0 is where are the lowest amount of pressure that can actually cause you to detect anything is at 0. We set that the 0 marker for the scale. Now, if you go into your book, I could go, let's see, page 406. The scale at the bottom is great. The scale at the bottom is wonderful. But the paragraphs are actually dead wrong when it says how the decibel works, which means the answers in the solution manual are also going to be wrong. The ones I have here are right in this book, but it's only on this piece, and that is how exactly does increasing the amplitude actually change the sound. Because it's a logarithmic scale, and I'll show you this in the next slide, you want to write this down. Increasing the decibel level by 10 means that it is 10 times louder. Our book says it takes 20 decibels to be 10 times louder. And that doesn't make any sense. I'll show you why in the next slide. Every book I've got over here on the bookshelf, 10 decibels is 10 times. Does that mean 5 decibels is 5 times? No. It's a logarithmic scale. 10 happens to be the magic number. Okay? So every 10 decibel increase is 10 times louder. So if I have something that's 40 decibels, and then something that's 50 decibels, It's only 10 decibels louder, but it's actually 10 times as loud. Okay? This move right here is times 10 on loudness. And from 50 to 60 is times 10. So what is for 40 to 60? How big of an amplification is that? That's 100 times louder. Times 10 times 10. What if it's 41 decibels louder? You need to use logarithms that we're not going to get to this year because we don't have enough time. Always going to be multiples of 10. It'll be really nice. It'll always be multiples of 10. But I'm going to show you this because I want to, so you know where it comes from. But you won't have to do it. You should know. Okay? So, we call the bell... Well, first of all, we have intensity that the human ear can hear. We call intensity naught, intensity 0, the lowest amount of intensity air pressure that's audible. Okay, anything lower than that cannot be heard. And so for any sound higher than that, it has some intensity I. I divided by I naught is then going to be some value from 1 or higher. Because if I naught is, if I is I naught, then I naught over I naught is 1. And so then we get 1. But if I have something that's, say, 10 times as loud, 10 I naughts, then this would be a value of 10. Or if it was 20 I naughts, if I had 20 I naught over I naught, then that's 20. Okay? And then because this scale goes, it's way too many values, we take base 10 logarithm of it, we go log, that's going to crush that scale down to something a little more reasonable, and we call this a bell. A bell is the logarithm of intensity received divided by intensity that's the lowest we can hear. But that scale actually ends up being a little bit too small, so we take it times 10 and call it decibel. Okay? Because 10 bells. Every 10 bells is a decibel. So now if, for instance, I receive a sound, let's say I receive a sound that is the lowest I can possibly hear. So then the lowest I can possibly hear going in for I would be I naught. What is I naught divided by I naught? 1. What's log of 1? 0. What's 0 times 10? 0. So I end up getting 0. So 0 decibels is the lowest I can hear. Now if I take this times 10, let's say it's 10 times louder. So now, how many decibels will it be if I put in something that's 10 times as strong? So 10 I naughts over I naught. Well, what's going to happen here? The I naughts cancel. What is log of 10? 1. What's 1 times 10? 10 decibels. So 10 times louder makes a 10 decibel change. And if I times it by 10 again, that would put a 100 in here. So 100, what is log of 100? 2. 2 times 10? 20. So every times 10 is 10 decibels. Not every 20 decibels is times 10. That makes no sense. Now the scale at the bottom of the page where it says 10 decibels, barely audible. Siren at 100 decibels, 70, heavy traffic at 70. That's all good. Those are right. But in the paragraph you'll read, it says, I'll read it to you, it says, a sound with a pressure amplitude 10 times larger is 20 decibels. No, it's not. Logarithms. Okay? Book is wrong. Answer key, solution manual online is wrong. You won't have to do the logarithm stuff. You will have to do questions like, let me go back, Doppler effect system. Yeah, 40 to 60. How many times louder is that? That's 100 times louder. If I put on earmuffs that reduce the decibel level by 30, then something that sounds like 50 normally, when I put the earmuffs on, what would it sound like? 20. And then it might say, well, what's 20 on the scale? Okay, so 20 is on the scale, but 30 is a whisper. 50 is a casual conversation. You'll have to go back and look at the chart what it comes from. Now, fun fact, a rock concert at 110, pigs can squeal at 140 decibels. Some people don't know how loud pigs are, but I grew up on a hog farm and I know these things. Okay, you've got to use ear protection if you're working with hogs, especially indoors. It's crazy loud. They can squeal louder than jet engines. Not kidding. It's amazing. Maybe. Whoa! It is a horrible sound. Anyway, we're out of time today. We'll start with a Doppler effect next week on Monday.